Hello, welcome to our audio slide presentation. In this presentation, we will talk about isogeometric shape design sensitivity analysis of stress intensity factors for curved crack problems. This slide explains the significance of the geometrical description of the crack face in the interaction integral formulation for curved crack problems. In the interaction integral formulation, the crack tip local coordinate system is defined by tangential and normal vectors of the crack face at the crack tip. The auxiliary solution field, which is a crack tip asymptotic solution, is a function of crack tip local coordinates r and theta. In the right figure, the black line indicates the crack face and the blue line the approximated geometry, which is the FE mesh. Also, the red line is an exact tangent line at the crack tip, and the blue dotted line is an inaccurate tangent line from the FE mesh. Evaluation of the stress intensity factor using the FEM may lead to inaccurate results since the auxiliary solution field is inaccurately defined by approximated geometry. In curved crack problems, we consider the crack face integral in the interaction integral formulation. Also, the crack face integral includes the normal vector information on the crack face. This slide presents a numerical example of stress intensity factor analysis in a circular arc crack problem. The exact solution of stress intensity factors K1 and K2 are given. Note that the quadratic NURBS describes the exact geometry of the circular arc. However, the Lagrange polynomial represents the approximated geometry, which gives us an inaccurate definition of the crack tip local coordinate system. In the table, stress intensity factor analysis results by the isogeometric analysis using quadratic NURBS basis functions are compared with those by the conventional finite element analysis using quadratic and linear basis functions as the angle beta is increased. Linearly approximated crack geometry results in an inaccurately defined local coordinate system, which leads to an inaccurate evaluation of auxiliary stress and displacement fields and consequently results in significant errors in stress intensity factor analysis. Although the results of FEA are improved by employing the quadratic basis function, they are still inaccurate compared with those of the quadratic isogeometric analysis. The DSA of the interaction integral is divided into three parts. The first part considers the design dependency of the actual solution field, which is suggested by Chen et al. In 2001. And the second part considers the variation of the crack tip local coordinate system due to crack orientation change. By considering a smooth design variation, the material derivative of the tangential angle theta c can be attained by multiplying the curvature and the magnitude of design velocity at the crack tip. Also, the material derivative of matrix T, which performs transformation between local and global coordinates, is derived. The third part considers the design dependency of the Q function and the auxiliary solution field to reflect the non-constant design velocity field in the interaction integral domain. Thus, by using the chain rule, the partial derivative of auxiliary solution field is derived, and the x1' and x2' are derived by considering the rotational effect v theta tilde and translation of the crack tip vc. The figure on the left shows the design variation of the circular arc crack. The design variable is selected as center angle beta, and the perturbation amount is 0.1% of the original center angle beta. Also, we obtain the exact solution of sensitivity by differentiating the exact solution of stress intensity factors with respect to beta. The table below compares the sensitivity obtained by the developed analytic method with the exact solution. Linearly approximated geometry is used in the linear FEA. In the quadratic FEA case, the agreement is much better than that of the linear FEA case, but still has significant errors due to the inaccurate curvature information. In the quadratic IGA case, we can accurately consider the effect of crack orientation change from the exact geometrical description. Therefore, the DSA results are much more accurate than those of the FEA cases. This is the conclusion of our presentation. First, the crack tip local coordinate system is defined by the exact normal and tangential vector, which enables us to obtain accurate stress intensity factors. Second, we derive the analytic sensitivity expression of stress intensity factors, considering the shape dependency of Q function and auxiliary solution field, which reflects the non-constant design velocity field in the interaction integral domain. Also, the variation of crack tip local coordinate system is considered. Finally, through numerical examples, the verification of the exact description of curved crack geometry enables the isogeometric method to give more accurate results of DSA in curved crack problems. Thank you for your attention.